Now I would like to invite Somya AI. Somya AI team is led by Vedpal Jangir, who holds masters in AI from IISc, and Rajates. This team is leveraging their deep research background, specializing in building advanced AI solutions for Indian languages, including zero-shot text-to-speech models to ensure voice technology is accessible to diverse linguistic communities.
Okay. Hi everyone. I'm Ved. I was I'm Vedpal Jangir and he's Rajat. We both are previously in IISc as research scientists. Okay, this is our problem statement. We took from there here. So we have to build a multi-language TTS synthesis model, and the focus on like efficiency, reliability, and efficiency, scalability, and reliability. Plus our adoption was like I reformulated the entire problem as a autoregressive token prediction models, so it can be like adapt to any other languages like easily, and plus it can stream in real time also, and there are other optimization also there. So here are our objective to build this one. So first one is a multilingual speaker. So the current LLM paradigm is like they are heavily pre-trained and already is there. So we thought we build on top of that because we are heavily resource constrained. So we took a already pre-trained semantic tokenizer, speech LLM tokenizer model, and then a bytecode tokenizer. Second objective was a zero-shot cloning. So earlier in round one, we did single stream token, and the constraint was okay, you have to do the zero-shot cloning for accent and style transfer, as there. This one was the metrics for that. And third one was the efficient deployment. Like it can be deployable into any small models, like in a laptop and mobiles also is there. So that's all. That's also is there. Okay, this is our solution. Okay, this is something weird. Okay, so this was our solution, a token autoregressive problems like a token-based prediction models. We did a tokenizer of bicodec, and then we formulate the entire problem as an autoregressive token prediction problem. So it will solve kind of problems like you don't have to rely on like all the heavy rule-based language modeling, and you can take a pre-trained codec model that can tokenize the semantic and linguistic part and then put into the model, and that small model can regressively predict the next token, so it can be adapted in any languages, like for similar small dialect or their regional language with pretty less data because the heavy training is already there. For zero-shot cloning, we did earlier we did the single stream tokenization. Like in single stream, it will produce the semantic and voice tokens. But in this time, we separate both of them. So global token, audio and sound, like a speaker can speak multiple languages, but their sound is similar. So that will do the global token. And you can took a variable, either variable or either context constant. So we did constant part of fixed length, and semantic token can be variable that key how much user want to speak that this is the content, and that will solve the gradient context prompt context window exploding problems. Like earlier in F1 we also thought that, but in you don't have to like rely on like if you give a 30-second audio as a reference, then model automatically capture the 32 token because it's a pre-trained, and then do a conditional base on the semantic token part, like how it produced the semantic tokens and all that. And we did actually in novelty, you can say we took a Quen 3.5 5 billion parameter model, and then we extend this model for our Indian languages. You just need a embeddings layer on top of the model, and then stabilize the embeddings layer. And you can have to just 1 or 2 hour full warm-up training, and then you can in phase 2 you can do a full fine-tuning. Then it will completely stable, and then do a for Indian accents and Indian languages also is there. This is the system architecture we propose. So these above are the global tokenization, and it will took from reference audio. So what it will do pre-compiled. Like when you give this reference audio and the text in loading part itself, it solves the semantic and globalization tokenization in encoder part, and then model only left to predict the semantic tokens also. It don't have to do the audio loss function and all that. So this objective was too simple just to predict the semantic tokens. This is for referencing part. So it will precompile the globalization as a speaker part and then predict the token and then detokenize with the same tokenizer. Our evaluation is like we don't have proper evaluation suite. We use indic transliteration for text normalization, and I think from AI for Bharat, there are pretty good ASR models. The 600 MB models, pretty smart models. We did use that for ASR modeling, and these for MOS score we did in lab, collect the mean opinion score. The deployment efficiency is like 0.5 billion parameters, so it's much smaller model and can be deployable in anywhere, and it can be deployable in a laptop with 4 GB VRAM. And plus one more thing is for like adaptability and scalability. Like you don't need anytime 20 to 30 languages in a single model. You need one model with one small precise model with single dialect and single language. So you can, from this base model, you can distill it into a single dialect and single language model and can adapt in anybody. And it can train, our entire model can was trained on like single A100 GPU with like 8 or 10 hour entirety. So that's also there. Okay, these were the failed experiment, I can say. We did lot of experiment before come up with these results. I did first round I did that part, Llama 3 model, base model, and single codec, snake codec. So that was the objective in previous round. It will condition the reference audio and then predict the audio based on that part. But what it will do, it will took the reference audio in a condition part and expand the window size. So if you have like 30-second reference video, then there is no chance to predict next audio token. So that's a problem. And second, the size itself, it's a 3 billion parameter model, so it will training and all that, it will complex. And third was there is zero-shot cloning, it's not stabilized either, so that's also a problem. In second iteration, for zero-shot cloning hack, I did took randomly 3 to 6 seconds and preconditioned the objective, and then did the same, but results are almost similar. These are conclusions, like, yeah, these are same, whatever I explained you earlier. Thank you. Okay, if you have any questions, sir.
Can you show the architecture slide?
Sorry. This one.
Yeah. So actually, when we talk about the edge device, right? So because we are talking about pregnant women, they are very low resource devices. So when you talk about the codec encoder, right, and then finally you are using the speech LLM here, and then again the bicoder decoder, the decoder on the top of it, right? So my question is, like, suppose if we and I think the parameter is 0.5 billion, right? So
yes.
Suppose if we want to execute as a SLM, like a very short language, a very small language model on an edge device, and it's a low resource, so the internet is also very low, right? So you can't host it on, like, so my question is whether you want to host it on cloud, where each transaction, each call, each query will go to a server and then fetch the response, or you want to execute it completely on edge, on device. But you will have to keep in mind that these are pregnant women, these are from underserved communities, so they won't be having a posh mobile with heavy RAM and compute power. But at the same time, if for every query, if the query is going to a server and then fetching the response, that is also bad, because the internet is not there in deep root villages. So how are you going to solve the problem of whether you want to host the complete model, the complete the text TTS model on the device versus on a cloud instance, but then at the same time you will have to worry about the internet cost. So yeah.
Okay. Sorry. I missed a lot of things. First, the model latency or model inferencing speed is the real-time factor is 0.42. So it can, if in a 8 GB of GPU RAM memory, it can produce 100 seconds of audio in 42 seconds. But it can go real-time on CPU basis also. You don't need GPU for that because the model is too small and it can fit into a RAM also. Second part is the internet and all that. You can we did with VLLM deployment, so you don't need to rely on internet or anything. You just build. You can deploy easily on edge devices. Plus, we actually did a lot of optimization. Like the model footprint are very low if you do the quantization and or other optimization. We didn't train on FT32. We did on F16 or BF16, and because int 4 or int 8 they are unstabilized the training, so that's not good. But and also there is a flash attention module for training. Optimization is good, but really not good for inferencing, so that's also a problem. But you can put in any edge devices and it will do great. For training part you need server, like it was single GPU. 8 GB GPU will be fine, or 16 GPU will be great, and it can adapt any local dialect or local language in like 3 to 4 hour data and can go, because the embeddings layer added into the top of the pre-trained model, they need to stabilize, and then you can do, it's already 0.5 model and you can train LoRa on top of that part. Initially when we started this one, I thought of F5 Indica 5 as you guys did, but the point is it's a diffusion based model. You can't do LoRa training on that, so it's adaptability problem was there, so I completely scrapped that part.
But you need to consider the fact that their mobile phones are not like up to the mark. So when you talk about even 0.5, forget about 0.1 billion parameters also, I don't think it's going to solve the purpose, right? Because and many of them would have feature phones stuff, right? So I don't think it's going to solve the purpose. Like,
okay, two things more I address. First thing, at least you need a laptop. 4 GB VRAM you need at least if you want to do the speeding and all that. But if you want to really go for edge devices, you need distillate model from. Take this model as a base and then go distillate model. That can be like 50 MB, 200 MB for specific dialect and specific language, not the entire 22 languages. I mentioned that, but probably. And second part is, sorry. So, okay, I select speech LLM because the application point of view. Let's say we don't want text to speech only. In voice bot or chat bot, there needs to be intelligence that not only produce text and then speech. The LLM itself can be trained on your user data and then can come back with you answers, not the just text speech part. That's why I use LLM, because application wise it was be much more efficient because it's already pre-trained, so we don't need to do the heavy pre-training lifting. So you can easily switch the LLMs and then it will produce the same result, because you just need to convert the text into phonetic tokenizer and then produce the actual answer into text part. So speech to speech model also it will be efficient if we put ASR 2 layer of ASR model, as AI for Bharat provide very efficient model for that. And second is normalization also is there, because I mentioned to forgot, there is a Indic transliteration library and num to num library for Indic languages specifically. They built it very good library, so that will solve the translation problem. So domain specific issue won't be there if you do that part.
Yeah, but if you're using AI for Bharat's translation model, that is some 63% accuracy. Accuracy is not very high. Another thing is my question is this Quen 2.5 which you talked about, it's a speech to speech LLM, right?
No, it's not speech. It's just a you can say transformer based model that will that will produce the semantic tokens, not speech tokens. They're like content that represented into text represented into how to speak.
Somebody must tell it what that semantic content is, right, for training. So where did you get that?
Bicodec tokenizer. We did that.
So what is bicodec?
Bicodec is like a neural tokenizer that will produce two type of tokens. It's global sound tokens and the content tokens as a semantic tokens.
Yeah, I'm asking you to train the bicodec, right? Or
We
did you not train?
No, we took pre-train.
If you took pre-trained, on what languages was it trained?
English. Sorry.
So then,
We stabilize for our Indic languages to expand the
what do you mean
embeddings.
by stabilized?
Because if we extend the model size, then
I'm asking you, what do you mean by stability of a model?
fine-tune the embeddings layer of model on Indic languages.
How much text did you take for that?
Entire data sets. It will take like 4 hours to stabilize the only 30% of model, and the entire fine-tuning will take another 8 to 10 hour data on single A100 GPU.
Okay, you said you brought it down to 0.5 billion parameters.
Yes.
What are the criteria that you use to bring it down to 0.5 billion?
It's subjective kind of. We did the testing part. If the model can be good with lower parameter, then we didn't train for higher parameters. So from lower to upper, we did that part. And these were the initial results. We are trying to bring down the also, but. Thank you.
Thank you, team.